Today we're going to talk about the deranged juggler. Now, that's just a nickname. What we're really going to talk about is counting a very particular type of problem, which is going to be a slight variation of what we've already done. So let's start by thinking about minimal juggling patterns. See, when we talk about minimal juggling patterns, it really answers the question, how many juggling patterns are there of a certain period, let's say period n, where our throws can be anything 0, 1, all the way up to n minus 1. All right. Well, we know the answer. N factorial. So, what we're going to do now is slightly tweak the question. So now our question is, okay, how many juggling patterns are there of period n where our throws are 1, 2, up to n minus 1? So in other words, we're removing the possibility of having a 0 throw. So it's a small restriction, and the question will be, okay, how many are there? How do we find the answer to that? Now, how do we think about this problem? Now, one way to think about this is in terms of our rook placements. See, we can think of the 0 throws. Those are the diagonal, right? That's 0 throw corresponds to a no throw, but in terms of the pattern, it's like, oh, you throw and it automatically catch, boom, same beat. So, all right. So what we're saying is, hey, it's like we're trying to count those rooks that we're placing. How many ways are there where there's nothing on the diagonal? So that's what we're after. Now, why are we calling this the deranged juggler? Well, it turns out that in terms of permutations, what does that mean? Well, it says that if you were to think of an ordering of something, you have maybe n people in a row. Well, what we're trying to do is rearrange them so that no person is back where they started. In other words, everybody had to move. That's called a derangement. Everybody changed their position. And so a derangement is what we're really counting. How many derangements are there? So that's why we call it the deranged juggler. All right. So how do we do it? How many are there? And what technique are we going to do? Well, it's going to be a little interesting. Our approach is going to be to say, hey, let's look at a particular fairly large collection of objects. So there's a lot of them. But instead of counting them, so normally what do? When we think of counting things, we're like, okay, 1, 2, 3, or, we can channel our inner count. 1, 2, 3, right? It's just like everything makes a contribution and we go up. But we can also weight things. In our case, when we talk about a weight, we're going to talk about things like a plus or a minus. So something that's a plus makes our count go up. Something that's a minus makes it go down. So when we tally it all up, what we're really saying is, okay, sort of like what's the net difference between these objects, the ones that are positive and the ones that are negative. Now, you don't only have to use plus or minus, but that's a fairly common one to do. Now, the trick is to think of the right collection of objects and to make it so that at the end of the day, you get what you want. In other words, the final count, that difference between all the pluses and all the minuses, will somehow be the right thing. In our case, the derangements. Okay. So I'm not going to motivate anything. I'm just going to give an argument and talk about how the approach works. So this is a nice small example. By the way, this method that we're going to go through, it's sometimes abbreviated as DIE, where the D stands for describe. We have a collection of objects. We're going to describe them. I stands for involute. We'll talk about what that means. And E says the exceptions. Again, we'll talk about that as we go forward. So we'll start with the description. What are the objects? Well, what are our permutations? One way to think about them is that you have like the symbols 1 through n rearranged in some order. So you can think of it almost like a word, where instead of using normal letters, we'll use these symbols 1 through n. And so we'll say, okay, so let's think about our words. that we can form. And we don't want any symbol repeated. But now we can say up to length n, up to and including that. So in other words, we can have shorter words, but we don't want any symbol repeated. Okay, so there's our description of our objects. So we have these sets of words. Now, what's the plus or minus, right? Because we say, look, some things are plus, some things are minus. We're going to weight it according to how close the length is, in some sense, to the length n. We want a full length. We don't want these smaller words. And at this point, you're probably thinking, you're right, we don't want these smaller words. Why are we including them? That'll become clear in a few minutes. So we're going to have plus or minus depending upon how close you are to n. If you're an even number of steps away from n, you're plus. If you're an odd number, you're minus. So that's what our weight is doing. That's that -1 to that power. Now, here's the beautiful thing. See, we have lots of pluses and minuses. And what we're going to do is we're going to start taking our objects and saying, okay, you two come together, and you two come together, and you two come together. We're going to pair as many of them as we can. Now, this is sort of where the word involution is coming from. So when we talk about an involution, it's a rule that says if you apply it twice, you get back to where you started. So boom, boom. And what happens is there's two possibilities. When you apply the rule once, you go to something different, and then you return back to where you start, so that you can sort of pair yourself with where you got sent to. So you get pairs. But it could be the case that when you map to yourself. So you don't really have anything to pair with. You're just by yourself. So the involution says there's pairs and there's things by themselves. So we want to take advantage of this notion of pairing. All right. What's the rule for pairing? What we do is we look at our word. And we say, all right, hey, word, nice to meet you. But then we say, okay, let's look for the smallest number where one of two things is true, right? Either you're going to be missing. So in other words, we wanted all the things from 1 to n. And so maybe like 5 is missing. Oh, okay, that's our 7. Or maybe nothing's missing. Maybe it has all the symbols. But we say, okay, look for that. Now, the other thing we look for, because that's one possibility, the second possibility is we say, great. Well, what if, look for the smallest number that's in the right slot. So maybe you're looking at 1 and it's in slot 1. Okay, that's what you want. All right, but maybe 1 isn't in slot 1. Okay, then maybe 2 is in slot 2. Or maybe 3 is in slot 3. So, okay, remember, smallest number that is missing or smallest number that's in the right spot. Now, why do we care about these two things? Well, let's think about, and we'll get back to this, think about what a derangement says. Nothing's missing, right? Because you have all the symbols from 1 to n. It's a full permutation, right? And nothing's in the right spot. So in some sense, this is like, hey, none of these things can be a derangement if you are either missing something or something's in the right slot. Okay, so essentially that says, hey, look at all these things that aren't derangements. Let's pair them up. Now, how do you do it? Well, suppose the smallest is something that's missing. Okay, we'll put it back in. But where? The answer, in the slot that it should go in. So if 3 is what's missing, we put it into slot 3. Now, it might be that as we put it into slot 3, everything above it sort of gets moved up by 1. But that's what we'll do. Now, if something is in the right slot, take it out, and then move everything down by 1. All right, so that's what we'll do. Let's work through an example. Examples are really helpful to sort of understand the process of what's going on. So let's look at the example with n equals 3. That's a reasonable example in that there's some things that are happening, but we can all put it on one page, which is really useful. And so what you see here are all the words which have length at most 3, no symbol repeated. Now you might say, wait, what's this one? Well, that's what we would call the empty word. So there's nothing there. Now you might say, wait, is that really a word? Well, yeah, it is a word. It's the empty word. Now, if you look at the symbol, you might think that looks kind of like a phi. Is that? No. It's not. It turns out it's from the Norwegian alphabet. It's a vowel, so something like and so you can say, hey, what's that? And you're like, yes, exactly, the empty set. Good. So empty word, empty set, nothing there. All right, so we have the empty word, nothing there. 1, 2, 3. All right. 1, 2, 2, 1, 1, 3, 3, 1, 2, 3, 3, 2, and 2, 3, 1, 2, 1, 3, 3, 1, 2, 3, 2, 1, 1, 2, 3, 1, 3, 2. All right. Nothing's repeated. Everything that we wanted to put in our objects are there. And we've also done something else. We've put in pluses and minuses. So length 3, well, that's the right length. That should be a plus because it's 0 away from 3. 2, that's 1 away from 3, so that's minus. 1 is 2 away from 3, so that's plus. And then the empty word, well, there's 0 letters, so we're 3 away from 3, so that's back to minus. So let's go through and do the whole pairing rule. Now, how does it work? Well, let's start. Start with our empty word. Well, what's the smallest thing? In this case, it's the smallest thing is what's missing, and it's missing a 1. So you put a 1, and it says, hey, that should pair with the 1. Now with the 1, you say, oh, wait a second, what do we have? Well, 1 says, look, the smallest thing is the 1 is in the right slot. So that you should take it out, and when you take it out, you're left with nothing. So in other words, the empty word and the 1 pair up. In fact, if you think about our rule, it says, hey, if the smallest thing that's missing, well, you put that in the right slot. But now you say, oh, wait, look at that new thing. Now the smallest thing is what's in the right slot, and you go back. So you see these things pair up. All right, so that's a pair. All right, how about 2? Well, 1 is missing, and so what we should do is we should insert 1 in the right slot. So we should put 1 in the first slot. 2's already there. So what do? Well, we just move the 2 over. So it would become 1, 2. So that goes over to there. Well, now what? Well, let's talk about the 1, 2. Again, 1 is the smallest thing in the right slot. Okay, take it out. That gets us back to 2. And we can go through and do similar things with 3. Smallest is what's missing, is just 1. We put in the right slot, so that means we have to move the 3 over. So 1, 3. And in 1, 3, 1's in the right slot. That's the smallest. Take it out. Move the 3 back, and there we go. All right, well, 2, 1 is the next one we haven't talked about. Well, smallest thing missing is 3, and 1 and 2 are not in the right slot. So that should say it should go to 2, 1, 3. So we're going to put the 3 in the right position. All right. In 2, 1, 3, well, 3 is in the right slot. Nothing's missing on the bottom row. Well, so we take it out. So that would become 2, 1. Let's see, how about 3, 1? Well, neither of those numbers are in their right slot. So 2 is missing. So we would insert the 2, where would we put it? Into the second slot, which means it would need to be 3, 2, 1. Okay, so that's going to go down. And then with 3, 2, 1, say, aha, look, the 2, that's the smallest thing in the right slot. So that goes up. With 2, 3, neither of those are in the right slot, and the 1's missing. So we put the 1 at the very start, right? Put 1 in the slot for 1. So that goes to 1, 2, 3. And of course, 1, 2, 3, you can pull out the 1. That goes back. And here, 3, 2. 2 is in the right slot. See, 2 is in the right slot because it's in the second slot. But 1 is missing. So put in the 1. So we put that into the slot 1, which would give us the 1, 3, 2. And that pairs back. Now, how about for 2, 3, 1 or 3, 1, 2? Well, the answer is we can't do anything with our rule because what's happening? Nothing is in the right slot, and nothing is missing. So, well, we just leave them as is. Now, here's the key, and this is why this is really cool, is we have these two exceptional cases. And what are these two exceptional cases? Well, there are permutations on 3 where nothing maps to where you started. They're the derangements. What about everything else? Well, everything else says we've got natural parents. And the key is when you look at how things pair, what do you notice? Well, you always pair a plus with a minus. Now, why? Well, that's because of the way we defined our weights, right? We defined it in terms of the length of the word. So if you add a symbol or you remove a symbol that adjusts the length of the word by 1, which means that in terms of that sign, -1 to the power, it changes it by plus or well, it changes it by 1 iteration, right? So it's going to negate whatever the sign was. And so what happens? Well, now we add up all the minus and pluses. We say, look, cancel, 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 plus, plus. 2. Which is what we want. Woohoo! Yeah. Okay, so let's do a little bit of summary. So we've already said this out loud, but we'll say it again. So our pairing rule has the following 2 important properties. The only things that don't pair are the derangements. Everything is in the wrong place, but everything is also there. And so there's nothing to pair with. The other important thing is that whenever we pair, there's a plus gets paired with a minus. And so at the end of the day, when we add everything up, all the pluses and minuses cancel off except the pluses with the derangements. And therefore, our final count will be the number of derangements. Fantastic. And the nice thing is, the derangements aren't so obvious how to go about counting them. But now we're just talking about words of some length, where we say, well, there's certain symbols, there's no restriction. They can be anything you want. Just pick the letters you're going to put in, arrange them in the right way, and life is good. So let's figure this out. So here we go. Number of derangements is our weighted count. And how do we go about our count? Well, we're going to count based on how long our words are. So we're going to add, so that's our big sigma here, adding up. K is going to be the word length. So we're going to add based on the length of the word. So add over all the possible lengths of the word. Our weight is always going to be plus or minus. So for each word of length k, they all have the same sign, so that's why we're putting them all together. So the weight is -1 to the n minus k. All right, now, how many words of length k are there? Well, what do we need? We need to start with our symbols, and we have to pick k of them. There's a total of n symbols, so we have n choose k. Those are the symbols which will be in our word. And then for those k symbols, we say, look at all the ways that there could be to rearrange them. If I have k symbols, there are k factorial ways for me to rearrange. So pick the symbols, rearrange them. N choose k, k factorial. And that's the number of words of length k, using the symbols from 1 to n, no symbol repeated twice. All right, well, let's clean that up a little bit. So it's not too hard to do. What do we notice here? Well, if you think about the n choose k, you can write that as in terms of the factorials. N factorial, upstairs, downstairs, n minus k factorial, and k factorial. So you can get some cancellation with the k factorial. So you say, beautiful. So you have this n factorial over n minus k factorial. Well, notice we're adding up based off of k. So k is the only thing that's changing from term to term. So we have a bunch of terms. We say, well, what changes? And the answer is the k will change, but the n will stay the same. It won't change. So since it's constant, we can pull it all the way out. So we're going to pull it all the way out, and in this case, we'll pull the n factorial to the front. So this is a idea that, hey, constants can pull out. So what are we left with? Well, we have this sum here. And now we're going to do a small little trick, which is called reindexing. In other words, we're going to change the name of things. Notice that every time that the k shows up, it shows up as n minus k. So we're going to introduce a new symbol, and we'll call it L, and we're going to say, look, n minus k is L. So everywhere where I used to see n minus k, I put in L. Minus 1 to the L, see that's there, 1 over L factorial. There we go. Now, the thing you might object to says, well, shouldn't we sum over n minus k? Shouldn't that somehow be the sum of over n minus L now? And the key here is to say, well, look, we're really summing over all the possibilities, and, well, there we go, right? Now, technically, I've been a little bit lazy here, and so let me be slightly more careful. And when we talked about these sums, we have to talk about the sums in the range where they make sense. So this is 0 up to n, and it's always been 0 up to n. We just sometimes suppress notation. And here, it's still going to be 0 up to n. So what you should think of is when k equals 0, L equals n, and we keep going all the way up to when k equals n, L equals 0. So it's just essentially, instead of ordering 0 to n, we're going n to 0. So we still add everything up. Okay, well, great. An answer, I guess. But as we stare at this, we start to say, wait a second, something feels a little bit familiar here. Very familiar. If you remember back to good old calculus days. Now, you might say, those were great days, but what does calculus have to do with this? You might remember there's this idea of Taylor series, and in particular, there's this nice fact, e to the x is the sum over all L, and I'll put here 0 to infinity, and of what? X to the L over L factorial. That's it's a very nice fact, which has a lot of nice applications. Now, you might say, hey, it kind of feels familiar, right? We got the L factorial downstairs, we have something to the L. And so one thing we can say is that e to the negative 1, well, that's the sum, 0 to infinity, minus 1 to the L over L factorial. So, how does that help us? Well, these pieces here are the same. Minus 1 to the L over L factorial. Now, what's the difference? Well, the difference is how far do you go? Here, we're going to stop and say, look, we're only going to go to n and stop. This one says, don't stop. Keep going. Keep going all the way. Well, what's the result? The result is, of course, this is not the same thing as e to the minus 1, but it's close. And it turns out, for large n, it's very close. Now, the reason it's close is that the n piece, what I would call the tail of the sum, is very small. And so we say, aha, this is very much like n factorial over e. And in fact, that's a great answer. It turns out, if you take n factorial and divide by e, it won't be a whole number because e is a very strange number. It's 2.71828. So n factorial over e is a whole number. But, if you now round it to the nearest whole number, that's the right answer, assuming n is large. For example, at least 1. So for large enough n greater than or equal to 1, if you just take n factorial divided by e and round, that's how many derangements there are. That's such a cool answer. It just says, hey, it's amazing, right? Wow. And so one of the things that it does tell you, that you can think about this in terms of like a probability. It says, okay, what's the likelihood that you have a derangement? And so the answer is, well, our likelihood that we have a group of, say, n people in a row, we have them all jumble around in some way. What's the probability, how likely is it that nobody went to the same spot? So, well, there's n factorial possible ways they could have ended up, and there's n factorial over e ways that they could have ended up where nobody got back to the right spot. So by taking that ratio, we can say that the likelihood of a derangement is this number 1 over e. And so it's something that probably you wouldn't think about. How would that naturally show up? It's not so clear. But yet, it's a beautiful answer. Beautiful answer. All right, so now we have the answer to our question. What happens if we take out one throw, right? Take out that zero throw, not allowing the zero throw. Okay, we have to divide by e. But of course, we don't have to take something out. So let's change our question. Let's put something in. So instead of the question where we only go from 1 up to n minus 1, now let's ask how many juggling patterns appear to n, which uses the throws 0, 1, all the way up to n. Now what's different here? See, now we allow both 0 and n. We've actually added a throw as compared to the minimal juggling patterns. Now how should we think about this? Well, in terms of the rook placement, what happens is you say, well, where do 0 and n lie in terms of the board? They actually lie on the diagonal. Both of them do. So if you put a rook on the diagonal, you also have to make a decision. Is that going to be a 0 throw or an n throw? So every diagonal gets 2 options. Everything that's off the diagonal, okay, that's just the one option, whatever the throw needs to be for things to work. So what's the count? All right, well, one can make a wild guess and say, well, when we took away a throw, we had to divide by e, but now if we add a throw, it should be multiplied by e, right? Well, that would be nice, but let's see what it actually is. Okay, so a little tiny bit of notation. We're going to call the derangements of 1 up to L d sub L. All right, so here's the claim. What we're trying to count is equal to the following sum. We're going to add up from 0 to n of n choose k, 2 to the k, and the number of derangements of n minus k. And at this point, you're probably thinking, what? What's going on? Okay, so let's explain these pieces one at a time. The first thing that often you want to think about is you're adding, and there's this index. Well, what does that index correspond to? So another way of saying this is, what exactly is this thing calling k? So what we'll have is that k is going to be the number of rooks on the diagonal. All right, well, now we start thinking, okay, so I have k rooks on the diagonal. Now, there's n places that are on the diagonal, and I'm only going to use k of them, so I have to figure out where to put them. So the first term, this n choose k, is going to say, well, pick your rooks on diagonal. So in other words, where on the diagonal are you going to put things? So there's n possibilities, you need k of them, there's n choose k. So we put our rooks down. So maybe we have 3 rooks. There we go. There are those 3 rooks. Now, what comes next? Well, we'll come back to this 2 to the k term. And I want to focus instead on this d sub n minus k. What do we have? Well, once you've placed the rooks on the diagonal, you say, look, those remaining rows and columns where the rooks came from are out. And so we can cross them all out. And if we do, well, what's left? And the answer is not much, but there are some things left. And in particular, if we just came up here and marked on this board what was left, what we would see is the following. Now, what is it? It's a little 3 by 3 board. So it's a smaller board. The size of the board, well, see, we've crossed out k rows, we've crossed out k columns, so it's an n minus k by n minus k board. We start with n by n. When we cross out those rows and columns, we're left with n minus k by n minus k. And notice what's true. We can't put anything on the diagonal in that smaller board because we've already placed all the rooks that we want. Which means that when we put the rooks down on that smaller board, it has to be the case that it must be some kind of a derangement going on. So we're back to a derangement. Ah, perfect, perfect. So, okay, so we can put the rooks down in some fashion. So there, for example, is one way to do it. All right, so this d sub n minus k says, okay, pick the remaining rooks on the subboard. But remember, I'm not going to write all this down, but remember that none of these go on the diagonal. All right, now the last thing you might say is, okay, what about that 2 to the k term? Well, that comes from what we say up here. Namely, that anything on the diagonal, we have two options. So once we have these rook placements, we say, okay, however many things are on the diagonal, for each one of those, we have 2 to the number of that, different juggling patterns that are going to happen. So this 2 to the k is really just capturing this idea up here. So that's all our pieces. All right, so now we have it sort of deconstructed, and we say, aha, an answer. We're done, right? Well, we can do a little bit better. Okay, so let's see if we can't make it look nicer. Not that this looks bad, but maybe we can make it look nicer. So we're going to do some manipulation. All right, our goal is really to say, let's clean up our expression and see if there isn't something more beautiful lurking underneath. Not that the expression we have is wrong, it's just sometimes with a little bit of gentle massaging, we can get our expressions to look more beautiful. And so let's see what we can do. All right, well, we have our initial sum, 0 to n choose k, 2 to the k, and then this d n minus k. Remember, that's the number of derangements of n minus k. Now, what we're going to do is replace things with known expressions. So, for example, n choose k, we can write that in terms of these factorials. So, namely n factorial over n minus k factorial times k factorial. And the other one is that the number of derangements, well, we have a formula for that. And they might say, yeah, n factorial over e, but actually we have a more technical formula. This n minus k factorial, and then this sum, L equals 0 to n minus k minus 1 to the L over L factorial. All right, great. We've got a start. Now let's work on cleaning things up. Some things are pretty easy to clean up. The n minus k factorials, well, those will cancel naturally. So, okay, that's one thing. Another thing we can do is this n factorial. You see, the n factorial, it doesn't change at any point in our sum. So we can put that on the outside. On the other hand, this 2 to the k over k factorial, we can do the opposite, and we can move that into a sum. And so in other words, we can just sort of put our two sum symbols, squish them next to each other. All right, so doing some cancellation and moving things around, we get that we are now at the following. This is n factorial, the sum, 0 to n, sum 0 to n minus k, and we have different indexes here, so it's a double sum. 1 over k factorial times L factorial, 2 to the k minus 1 to the L. Okay, that's interesting. I think that's it better, and it feels a little bit nicer. But we could do even better still, and that's going to be the key. So how do we go about going even better? And for that, we're going to have to do essentially what we would think of as substitution. So let's take a look at what we have. So what's going on here? So currently, this is what we're doing. We can think of it as our k and our L. So as k and L run over the indices, they run over these individual points. So I should have marked here. I'll do it really quickly here. Here is n, here is n, and over here is 0 and 0. So notice that k goes from 0 up to n. And once you know k, we say, well, look, L goes from 0 up to n minus k. So in particular, the further over to the right you are, the lower that L goes to. So essentially, what's currently happening with our sum is that we're adding up by adding up the columns. So we're going from left to right and then from top to bottom. Now, is there a different way for us to add? And what would that be? And the answer is yes, obviously. Otherwise, we wouldn't have gone down this rabbit hole. So how are we going to do it? So instead of doing the columns, we're going to do diagonals. So that's the main idea, is now we're going to add up over diagonals. So how does it work? Well, essentially, it's substitution and multivariable substitution, but for sums. So what we're going to think of is that for every pair, KL, I'm going to associate with the new pair, thinking of it as S minus T, T. Now, how should you think of this pair S minus T, T? Well, what S is measuring is how far over we're going. All right, so there's S. And then what is T measuring? Well, T would measure how high we go. And now we say, okay, look, if I want to get the same set of points, in other words, I want to add over everything, S will go from 0 to n. So from this diagonal to that diagonal. And then given any particular S, where does T range from? Well, see, if I'm at 0, I'm going to go from 0 to 0. Whereas by the time I get out here, I go from 0 all the way up to n. And so T goes from 0 to S. So by carrying out this particular substitution, we can get some nice things going on. Now this tells us here what's happening to our indices. Where do they go? And notice we also can say, look, here we know K is S minus T and L is T. So we're going to carry all that through. And what do we get? Well, we get the following. So again, the n factorial comes down. Our sum is now over S and T, but slightly different bounds, so that's okay. We're still adding up the same number of things. We're still adding everything up that we wanted to add up. We're just doing it in a different way. Everywhere where we saw a K, you put in an S minus T. Everywhere we saw an L, you put T. Now, how does this help us? And here's the cool thing. You see, we're very, very close to a binomial coefficient. Very close. How close are we? Well, if we replace the numerator with an S factorial, it would be a binomial coefficient. So we put an S factorial up there, and then here we'll put a 1 over S factorial. See, these cancel out. So multiplied by 1, we can always do that. And now you're like, okay, but how does that help? Because it seems a lot of stuff has disappeared to get down to this next line. Well, here is sort of the great aha. What's going on? Well, this is the sum, 0 up to S, of S choose T times 2 to the S minus T minus 1 to the t. Does that look familiar? It should. It's the binomial theorem. This is the same as 2 plus minus 1 raised to the power s. So this is, college algebra stuff almost. So we say, aha, I know how to figure that out, because 2 plus negative 1, I learned that a long time ago. That's 1. And 1 to a power is 1, which means that all this stuff simplifies really nicely, and it goes to 1. So our final answer is n factorial times this sum, s equals 0 to n of 1 over s factorial. Now you say, that's really close to what we had before, isn't it? It is. It is really close to what we had before. Well, except you don't have that minus 1. So what we can do is the same idea. We can say that E is the sum from s equals 0 to infinity of 1 over s factorial. So this right here is approximately E. And therefore, our final answer is about n factorial times E. Wow. So it did turn out that when we took away a throw, we divide by E. When we added a throw, we multiplied by E. It kind of feels right. It's beautiful symmetry, and it's a really cool answer. That took us a little bit of work to get there, but I think it was worth the journey. All right, well, that was some good stuff, and we'll keep it going, so make sure you check back in.